Welcome everyone to our 9th session of Tech Tutors East Africa. We are happy to have you here. And on today's session, we'll have Howard Frederick, who will take us through a tutorial on how do I create a flight plan for an aerial survey sample count. Howard Frederick is a conservation biologist working with the Tanzania Wildlife Research Institute as a research associate. Howard has specialized in aerial surveys of large mammals, GIS and remote sensing, and conservation education. He has been involved in training aerial survey teams and in collecting and analyzing critical survey data, such as that of the green elephant census, while working as a technical advisor for Vulcan. Welcome, Howard, and thank you so much for your time. You can start whenever you're ready.
All right. Thank you for that. So I'm going to be following on from what Richard talked about last week with he was talking about the overall setup and planning for these kinds of aerial surveys. And he gave a lot of information about how to choose the area of the survey, thinking about things like precision and some of the technology that's used. He was giving a very large overview of a lot of very, very interesting sections about thinking about these surveys in general, and then some of the more specifics. But I'm going to be getting into the real specifics of how we actually do a flight plan, meaning getting to the point where you've actually got something you can put on a GPS, an actual flight plan or route that you can fly an aerial survey with, and what some of those data would look like. So this is a much, much more detailed talk. I'm going to try to go through all the overview of how you set up the strata and the transects and then the flight plan in about 30 minutes. And then we will have time for hopefully a lot of chats towards the end after about half an hour. So I just want to very quickly review a couple of the things that Richard talked about. So in fact, what we're trying to do with an aerial count, and here I'm talking about sample counts, but I will make occasional reference to things like total counts. And at the end, we can talk about some of the other methods that some people use. But what we're trying to do with an aerial count is cover a very, very large area, usually a 50,000 square kilometer or 10,000 square kilometer large protected area that you can't cover with the ground. You could not reasonably cover it with a ground method quickly enough to actually do the job properly. It's relatively cheap to use aircraft, even though they're expensive to fly them per hour. The cost when you're looking at a very, very large area like that is actually relatively cheap. We are usually looking to count wildlife species, large mammals, things. Richard mentioned that they see things the size of the size of a cob or an impala on up to the size of an elephant. We're also looking for livestock like sheep and goats, donkeys, cattle, and other human activities like the presence of agriculture, roads, and any other target of interest. In particular, there are things that might be of interest to law enforcement in an area where you're working. And you may not even necessarily be interested in trying to get counts and actually try to get an estimate of the animals, but you're also trying to figure out the presence and absence of some of these things, which may mean a lot for law enforcement or may mean a lot for the conservation of animals in the area. The other thing which we need to think about very carefully is long-term data sets, because we are not only looking at data that were an immediate count, say, oh, we've got 25,000 wildebeest and 6,000 elephants in this area, and here's the map. You're looking at the trends, and this is the data library that we have at TAWIRI in the document room, where we have almost 60 years, actually 55 years, I think, of wildlife data. These are the raw data sheets that were collected in aerial surveys from like 1976, I think is the oldest one on this shelf, onwards. So this is a long-term data set. And what we're trying to be able to do is actually have things like this graph, which shows the trends in the wildebeest population, the Serengeti, in particular the migratory wildebeest population from 1955 onwards. And these long-term data sets are incredibly valuable for planning and for conservation of the species. The other big output that we have are maps of distribution. And I know a lot of the conservation managers, they often go straight to the maps when we produce a report. Where are the animals found? Where are they found in the greatest densities? This is the style of report that we're using at the Conservation Information Monitoring section at TAWIRI these days. which shows a survey boundary, and you're going to get a lot closer look at this in a few minutes. But the gray areas are outside the survey boundary. Everywhere within this pink and blue lines was flown for an aerial sample count. Within that, the little black dots show the places where we saw sable antelope. And the colors, the darker and darker oranges, show the density, the relative density of the sable. So high densities here in the western part of Ruaha, and very, very low density, very scattered observations of sable in Rungwa Game Reserve in the north here. When we get set up to do a survey, and the first thing you think to yourself, right, I need to get some transects out here. We need to actually sample the landscape. You might be lucky enough to have really, really firm orders and say you have to look at the specific area and you have to repeat a survey that was done before. And I'll be talking about fairly defined survey areas like that. We're not going to get into when you're having to go into an area where you have no information whatsoever, but you're often working with old information. So for example, this is one of the older surveys that we have on the shelf in TAWIRI, which was done by Ian Douglas Hamilton back in 1976 over the Selous census zone. And on the right over here, you can see one of the hand-drawn maps that was used back at that time and the grid that was overlaid on it. This is the dotted line shows the boundary of Selous Game Reserve and of Mikumi. I want to say national park, but I'm not actually sure it was a national park back then, but the Mikumi National Park in the north here. Sometimes you have very, very old survey boundaries that you can use as a foundation. More recently, for the same survey zone, you'll start off with a very, very up-to-date set of survey boundaries that cover the entire survey zone, and often you're simply asked to repeat a survey of that area. So here we're looking at the map that was used in last year's survey, showing the new Nerari National Park, which covers a lot of the old Selous Game Reserve, the remainder of the Selous Game Reserve, which was not included in the new Nerari National Park, Mikumi, and then some of the other protected areas, with the gray line here being the edge of the survey boundary. Nothing was flown for actual survey outside of that. After flying the survey, and this is the same area, this is the kind of track log that you're going to end up with. Having planned your flights and having flown, you downloaded all of the GPSs at the end of every flight. You end up with this extraordinary mess of spaghetti, which is all the flights that actually happened. You can see the very straight lines where all the transects were flown, where all the samples were taken. You can see places like the survey bases themselves. And in this map, we've got 3. You can see the aircraft were all taking off and landing from Matambwe in the north, the Kuyuseka Maganga in the south, and the Kilambaro airfield over here in the west. So you've got a complete record as you download your GPSs. And this is having done your flight plan, this is what the pilots end up bringing back to you from the GPSs. So these are the end results of having flown a sample count. I like to point out in some areas here, we have some kind of squiggly lines, which don't match the same dead straight sample lines that were flown here. These are areas where a reconnaissance flight was done in a very low density area, just looking for large herds of wildlife. It wasn't part of the regular sample count. It was known to be low density, so they flew just to see what was present. In contrast, this is a total count of the Serengeti National Park and ecosystem. This is the same scale, about 100 kilometers over a couple of inches, about 5 centimeters across your map here. And you can see the intensity of flying that was done out of the center of the Serengeti National Park. There was 700 meters spacing in some areas because we were trying to hunt and find every single elephant that was available to be seen in the entire national park. Not a sample count, but a total count. And you can see how much more flying. It costs about 3 times as much per square kilometer to fly a total count, and you only get 1 or 2 species out of it. And Richard covered the principles between of doing a sample count compared to doing a total count last week. So I'm going to give a quick overview right now about the principles of setting up some of the units that Richard talked about, such as strata, which are the blocks, the individual sample strata where you count inside, the individual transects, and then the flight lines themselves, the route. And then I'm going to go through examples in QGIS, showing the specific steps that go into that. I have not had a chance to put together a whole handout on this yet, but I'm aiming to have this on my on either the Transect Tools website or actually send it directly to Tech Tutors, to WildLabs. So I actually have a checklist of the steps to follow in QGIS. This presentation will also be available online. You'll be able to follow a lot of the steps directly from there. But I haven't, it would just have taken too long to try to do a click-by-click example here, but we'll be able to do that with videos in the future. So strata are the individual blocks that you fly once you've actually settled on your overall survey zone. And within these areas, having decided on the total survey zone, and as I showed you before, you've often got a survey zone that you need to, this entire survey area, for example, the Serengeti ecosystem or the Sulu-Mikumi Nyerere ecosystem. Within there, we're going to be setting up strata, which are blocks that are flown, usually often by one aircraft, with an even distribution of wildlife, something that you can do in a fairly short amount of time, so that there's very little movement of wildlife within or between blocks, between these sample strata. And they often use terrain and rivers and the wildlife distribution maps to define the boundaries. And the main aim here is to be able to sample a stratum where the wildlife are not going to be moving to an adjacent stratum very, very quickly. So you have a chance to get a snapshot of the wildlife very quickly within that one area. Within those strata, we set up transect lines, which are those very straight lines that we saw in the previous maps. These are the lines along which you're looking, the rear seat observers are looking in the left and the right as you fly. They are set up across ecological gradients so that you are flying from an area, typically an area of relatively low density to maybe an area of high density, area of low density, but each transect on average should have approximately the same density of wildlife. A lot of the flying and setting up that we do, the flight planning and the logistics around are about setting up the environment for the observers in the back of the aircraft, because the people who are gathering the data are having it's a very difficult job, and fatigue is a real issue. So each transect should never be longer than about 25 minutes of flying time, and ideally less than 20 minutes, which ends up being about 60 kilometers of flight time at the speeds that we fly. Transects are usually set up east-west where possible to minimize the glare. If you're flying north or south, then you often end up with the early morning or late afternoon sun hitting the window, and it can reduce the amount of visibility that you have. But the other considerations, such as ecological gradients and maximizing the number of transects, can be more important. So what we're looking at here is a map of Tanzania. And I'm going to be giving some specific examples about how the flight plan is set up for the Katavi, Ruaha, and Rungwa Rukwa ecosystem in the west of Tanzania. That's inside the red boundary here. Zooming in there, this is an ecosystem where we've done aerial surveys for a very long time. We've got areas that we've surveyed for decades now, and you can see what I'm showing in here, having zoomed in, is the area of the national parks, which are in dark green, game reserves in the orange. The lighter green is game controlled areas, and then we have nature reserves. This is from a few years ago, and some of these areas have already changed because we are redefining some of these landscapes. But this is the kind of thing, if you're looking at your priorities, usually national parks and game reserves being the area of highest protection in Tanzania would be where we'd make sure we want to maximize our effort and make sure we cover them. I've also put the terrain, a shaded terrain layer here, showing some of the other limitations that you'll typically face, which are areas of steep mountains, such as this area here in the northwest of Ruaha. I haven't got the lake indicated here, but you can see this very flat area is actually a lake boundary, and there's a very strong escarpment along it. And then just on the inside of Rukwa Game Reserve and Lakwati Game Reserve. So the terrain, the protected areas, and often the rivers are going to be the things which define the natural boundaries and the administrative boundaries that you need to think about when designing a survey. Something which I'm not going to go into, I don't know how much Richard covered in this last week, but the budget often is the thing which determines so much of the logistics of what you can do. The availability of resources, including money and the aircraft, determine what you can actually fly. This area that The polygon that I put over the top of this previous view is, and I'll switch back to that briefly, shows the area that was decided to be flown before this survey in 2018. So we were able to fly based on our budget, based on the available resources, within that gray boundary to cover the entire survey zone. So you can see that the survey zone covers the entirety of the national parks, such as Ruaha, such as Katavi, and the key game reserves within this area, Rukwa, Lukwati and Piti, Rungwa, Kizigo, and Muhezi. And thanks to interest from some of the donor, and some previous distributions of elephants that we've been looking at, we realized we need to cover some of these corridor areas between the two ecosystems, as well as going up to Ugala Game Reserve. So we actually added in some additional areas to fly during the survey. But this is not different. This is the entirety. When you talk about the survey zone, this polygon, this dark boundary, this is the basic area where you're told sample within this survey zone. When we did the flight planning, looking at the terrain, looking at the distribution of wildlife, looking at the river areas, and looking at some issues of logistics, these are the individual strata with their individual labels that we decided to fly within this ecosystem. So you can see there was a stratum called RC, which meant Ruaha Central, RN for Ruaha North, RS for Ruaha South. These are just labels of convenience that we used when we were handing out flying assignments to the pilots and to the crews when they would go out every morning. So these are the strata within which we are sampling. We define our transects get defined within these strata. Not all of these areas were flown with transects. You can see this very heavy area of a lot of hills here and WS and PS, M1 and M2. So we couldn't do transects in those areas. We flew in there, but instead of doing a sample count, you can't fly when you've got a 2,000-foot climb across some of these hills. The pilots and the crews were instructed to go and try to find animals within those areas and map each location. These are the transects that we ended up with our flight plan. And you can see that each transect has a name a unique name, which belongs to the stratum that it's inside. So for example, we have RC01, 02, 03, all the way up to RC35. If I go back one, you can see those belong to RC. RN to the north of it has RN01 all the way up to RN37. So there are 37 transects within Ruaha North. Here, because we have river systems that define, I'm going to go back a little bit. With the terrain here, you can see this is actually a river valley in this part of Ruaha Central. There's another river valley, which is a bit more difficult to see, but it runs across this boundary between Rungwa and Ruaha. That's what has defined these transects. We know we needed to go from areas of low to high to low density by crossing these river systems, which is why these transects are oriented north-south. Over here in Ruaha West, we oriented transects east-west because of the terrain, because flying north-south meant that there would have been a very strong gradient. You would have been climbing, doing a very strong climb, several thousand feet going north and descending several thousand feet going south, which is really difficult to fly. So in fact, logistics overwhelmed all other considerations for flying here. But we also knew it was relatively low density, so it was less a concern for orienting it across a gradient. And this is the flying that was done at the end of that survey. You can see all of the very, very straight north-south lines here for the sample counts, and these kind of squiggly lines where you're hunting and looking for animals within some other areas, such as this one here, these two mountainous areas, and especially these areas up here in the hills. You can't even see the turns we were doing. They were so tight that all of the areas were covered by sample count. The budget also determines whether you can afford to be flying a 5-kilometer spacing, as we were down here, or a 10-kilometer spacing for this area where we knew it was fairly low density and it was a lower priority. So we flew 10-kilometer spacing between the flight lines. When we define our strata, we define from our overall survey zone, we then cut. So when you're first doing your flight, your strata, you're going to actually chop up that survey zone into the smaller strata, which you can fly as individual pieces. So I'm going to show you from first principles what I did back in 2018 for this area. We have our overall survey zone in the blue boundary now. And if we focus on this area just down in the south here, I will go over how we actually set up the transects within a single stratum. So this is the Ihefu area, the southern part of Ruaha National Park. It's a lot of low swampy areas. There's a wildlife distribution which runs across the center of it here. There's a lot of human influence in the south, so we knew that we were probably going to be doing north-south transects across this area. And we wanted to have something which is no longer than about 60 kilometers wide at its widest place for the transects. And here it'd be defined by this escarpment. Doesn't look like much when you look at it in this shaded view here, but believe me, it is really, really tough to fly when you get into it, when you're trying to fly up and down that in a Cessna. In QGIS, and I will go over some of the tools at the end, a list of tools. What we tend to focus with in a lot of the work that we do at TAWIRI is free and open source tools as much as possible. These tools are things that we can all have access to. We don't have to worry about licensing fees. They are increasingly easy to use and above all free, which we all like. But I will always talk about whenever we do training, whenever we do these share tools, they're going to be something which anybody can download. And that includes some of the Python tools and some of the R tools that we use for doing the analysis work. Everything needs to be something which we can pick up year on year without having to worry about licenses or people not having access to them. So this is all going to be happening in Quantum GIS, freely downloadable, and I will be including links to some of these shape files so you can actually follow along at your leisure at some other time as well. So within QGIS, having defined and added our survey boundary, you can split it using the split features tool. And what we're going to be doing is drawing a line, splitting along from one end of the polygon through the escarpment here across to the other side. As you use that tool, you draw a line from one edge to the other. You can see the red line being drawn here. When you get to the other side and right click, it ends up cutting that overall survey zone into one smaller stratum. And that is that stratum RS for Ruaha South that I indicated before. And the first thing that I would do, having done that, is use the measure tool in QGIS and check that if I do north-south transects, that they're not exceeding 60 kilometers in length. So again, we're trying to minimize the amount of fatigue. We don't want a transect to go for longer than 25 minutes because humans really have difficulty concentrating at 25 minutes, which is about the amount of time I've been talking for now. So I hope everybody's still awake. But this is that's one of the limitations that we have when we are setting up the transects. Having checked that, we now want to start, we want to create a grid using QGIS. So we use the create grid tool, and in the following pages, I'm going to be showing some screenshots of the menus that are out in the top menu bar of QGIS. So for example, here, when you go to vector, research tools, and then create grid, you'll see the menu or the interface, which I'm going to show on the next page. You can also sometimes use, and what I tend to use is in the lower left of QGIS, there you can press Control K if you're on Windows or Command K on Mac OS. You can click on then a keywords, like start typing in create grid, and you'll have access to the same tool, which comes up in the list of algorithms here. They get you to the same tool. Using that Command K or Control K shortcut is really, really fast for getting to a tool within QGIS. But I'm going to be showing pictures of the menu, the accessing them by the menus here. This is the tool that we get for creating this grid. And what this is going to do is create a fishnet. If you've used ArcGIS, this is called the fishnet tool. And it basically creates a grid of even horizontal and vertical lines with a horizontal and a vertical spacing. Something which I forgot to mention earlier on is that the survey zones are usually set up with a UTM zone. a UTM zone grid, so you're using meters over the entire ecosystem. Because when we are doing a lot of our planning over very large areas, we often use latitude and longitude. When you are working with an individual survey zone, it's going to be in a single UTM zone. So everything is going to be in meters. And all of the tools that you build up until the point where you actually create the flight plan are going to continue to be in meters in this UTM zone. Usually you use when you tell it to create a fishnet, when you create this grid, you're going to use the extent of the whole area that you were looking at. I'm just going to jump backwards a little bit and show you. So when we were looking at this view here, I went directly from here to choosing the grid. I said, just make the grid over the area of the entire map canvas extent. So it automatically puts in all of these numbers here, which are just the boundaries of the top left and lower right corners. And I then tell it I'd like to have a horizontal spacing of 5,000 because I want to have a 5-kilometer spacing between my transects. I've told it a vertical spacing of 10,000, which doesn't matter because I'm going to be getting rid of some of these other lines because I only want to remain with the lines that go up and down. And I leave the grid CRS as the default, the coordinate system, because I want it to be the same UTM zone as my map canvas. When you click OK at the bottom of the screen, you're going to end up with a lovely grid, which is the basis. Now, this should start beginning to look familiar. These are the lines that we're going to start using to construct our transects. I won't go into the details, but you can click Edit on the new grid and start deleting features. And once you've deleted those east-west lines, you're left with a single grid of north-south lines, which cover your entire stratum. And you can see that they are all falling wholly within the area it's the whole map canvas here, but you make sure that, yep, everything covers the entire stratum that I'm interested in. So we're going to be trying to create transects which fall wholly within this stratum, this blue chunk in the south called Ruaha South. So next, you will select the stratum using the select tool. So you select that polygon. And then there's a tool called Clip, which you get from the vector geoprocessing tools, which will allow you, and I did a bad transition here. What it's supposed to show you is the tool, which create the next step of the tool here, where you would actually say the input is the grids, which is just called grid from our previous screen. The input would be the grid. You want to overlay it. You want to clip it with an input with another layer, which is the selected layers of your strata. Unfortunately, I haven't got that here, but I'll update it in the presentation I share. When you say OK, what you end up with is a new line. You're going to retain your old set of lines, but you're going to end up with a new one, which is called clipped. And now we have what looks like our transects, exactly the transects that we're going to be needing. They are clipped to the exact edges of the stratum, and nowhere outside of it is anything remaining. From here, we edit these lines. So again, in QGIS, you'll select the layer, this clipped layer. Something which is very important is to name. I think Richard mentioned that these transects are your fundamental sample units. So each transect has to have its own name, as I showed before, like RC01, RS01, R02, etc. And these are going to become the formal sample that you took across that landscape is that transect. They have to have a unique name. We name them on the basis of the stratum within which they fall. Here, for this example, I'm calling this stratum M instead of RS. And you can simply select the layer and select the field calculator option from the top of the QGIS toolbar. And within that, there's a little bit of coding magic here, where you tell it the stratum name. You're going to tell it to make a new field name called tran, which is a text, and you enter the name your transect, the name of your stratum number, had it to be two numbers long, starting with 0. So you end up with 0, 1, 0, 2, 0, 3, up to the number 10, in which case it just carries on as 10, 11, 12. The whole point of this being, don't worry too much about the details if you haven't done any of this coding in QGIS. This will be in the presentation. What you end up with is a very nice series of numbers, which are 2 digits long. So they sort nicely when they're in an Excel table. So M01, 02, all the way up to M23. We have 23 transects within this stratum. So at this point, we have managed, we've ended up with flight lines. We know that they are within that less than 60 kilometer setting, limit that we gave ourselves before. We can see that they are all within that they all fall within the correct survey zone, the survey stratum we're looking at. And now the first thing you do here is save this to you save this layer as a geo package, save it somewhere as a shapefile so that you retain these transects, because these are now part of your formal sample that you're taking within this stratum. So these now need to be saved as this line file needs to be saved for your later mapping and to define the length of the transects that you've used, because it's part of a formal sample count now. But the next thing we need to do is to be able to fly these. So you will use the layer, create layer, new GPX layer. And this is something which I must admit, I only discovered very recently. I often use some other tools which are more difficult to use. And to my great pleasure, I discovered this last night, instead of giving you a horrible Python tool to work with. So this is a really nifty system where you can actually simply say, create a layer as a GPX layer. It will add 3 new layers to your QGIS layers list, one of which is the routes. When you create it, you give it a name, and I do FP for flight plan _M for the stratum. And you will then simply start editing the route layer. You basically go forward and you click it backwards and forwards in the beginning to the end of each line that you want to fly. At the end of it, when you turn off the other layers, you will see that you have this lovely line which goes from the beginning of one transect to the end of it, to the beginning of the next transect to the end of it, and follows a snake pattern all the way to the very end. It takes you about a minute to set up each one of these. So now when you save this layer as a GPX file, you can, and this now becomes a flyable flight plan that you can follow in the aircraft. The pilot can follow this. It will literally tell them to fly to the first point, and then it will give them instructions to fly to here, to here, to here, to here, making it really, really easy. And you don't have to think at all about your navigation as you fly. So that was the whirlwind tour of setting up the flight plan. I'm going to talk just very, very quickly about a few of the other tools. Luckily, everything now is in QGIS these days. I'm also working with a GitHub. I have a GitHub site with some tools called Transect Tools, which has a Python tool for making automatically some of the flight plans, and also for creating those transects within the strata if you can add a model to QGIS. Garmin Basecamp is also really useful for doing flight plans, but I find it horrible. I hate the interface, so it's really annoying. And I use R and RStudio a lot to actually manage data, but that is a topic for another day. I got a request to talk a little bit about some of the equipment that we need for aerial surveys. And I just want to show a couple pictures and a list before we go into the Q&A. Radar or laser altimeter is the thing is absolutely required you have to test a radar altimeter if it comes with the aircraft, because they often don't work very well, some of these old things. Luckily, we can buy laser altimeters, which can be fitted to any aircraft. Also, these strut rods, which you see attached to the strut here, which actually define and you can see these are just fishing rods. We haven't even clipped off the little rings for the string and the fishing rods here. Which we did after this, I think after we took this picture, but they're just a basic fiberglass rod, but these define the counting area for a sample count. All of these things are available. There are places you can make them yourself, or you can also buy them from some companies in South Africa. Handheld GPSs and pilot GPSs are vital, as is cameras for the RSO position. These cameras, the only tricky thing to find, the cameras are usually very easily found, but getting these suction cup mounts, these are slightly special. And this is a Panavice suction cup mount. Again, I will share the details to this later on. The observers here can actually, when they come across a large group, they can take a picture by pressing a button with a cable release, getting a photo from their strip. And I don't know if Richard did this I missed part of his presentation, unfortunately, but I don't know if he did the 3-second test. Observers have about 3 seconds to count groups like this, and this is why we use cameras. So you've had a lot longer than 3 seconds. Any guesses as to how many buffalo are in this picture? I suspect that most of you are wrong. It's usually a lot more than you expect, which the human brain can count up to about the number 4 very, very quickly. You can see 3 objects, 4 objects, and instantly apprehend them all and remember the position. The moment we get beyond 4 objects, we have to start using a language system and counting using numbers, which is why using photographs is so important, hence the importance of the photographic equipment. So that was a whirlwind tour. I've got about, I think we have just enough time for some questions here. There are a lot of, I've had to skip over quite a few elements of some of but it would have taken simply too long to try to do the individual, some of the tools in QGIS. But I will try to do some screen recordings and step-by-step instructions for this later on.
Okay. Thank you for the presentation, Howard. Should we go to the Q&A bit?
Sounds good.
Yes. Okay. So we had a few questions that were on aerial surveys and some specific to flight plans. And one of the common questions that came up during registration is what safety precautions and ethical considerations should be taken when conducting aerial surveys?
So for safety, I think there's a question as well about some of the formal protocols that we use. You normally have to get permission from the civil aviation authorities to fly over an area. That often comes with when you're flying over protected areas. You usually have to work with the protected area managers. So in Tanzania, even though it's a government program that we work with, we have to formally notify the area managers, such as Tanzania National Parks, Tanzania Wildlife Authority, or Ngorongoro Conservation Area Authority, that we're going to be flying the area. At the same time, we give notification to the Civil Aviation Authority that we're going to be flying at low level, because ordinarily when you're a pilot, you learn about flying high and fast for safety. The only time the most dangerous time of the flight is usually when you're landing and you're going lower and slower when you're coming in to land the aircraft. You're always told, avoid low and slow. Low and slow is dangerous. But unfortunately for flying aerial surveys, you have to fly low and slow all the time. So we work with your pilots for training. You inform your aviation authorities where you're going to be. Make sure you have permission to fly those areas. You're not going to be interfering with anybody else who might be doing similar exercises. But pilot training and crew training for this kind of thing is extremely important for safety. And there are a number of protocols that we follow, such as the pilot is your number one person for actually making sure that you're flying safely. They will tell you if your flight plan, for example, is incorrect. They might say, I simply can't fly that area. Those mountains are too steep. We need to do something like a block count, which I think Richard mentioned in last week's discussion. Transect flights cannot be done in some areas safely. It might be that the winds are too bad, are too bad for that area. You may have to actually not even fly sometimes, wait for better weather conditions. But the formal status would be going through the Civil Aviation Authority, talking to protected area managers, sometimes the district authorities, and then doing flight planning and crew training around safety.
Mm-hmm. Okay, thank you. There was also a question on how do you avoid disrupting wildlife?
Disrupting wildlife. Yeah. Oh, well, I think somebody also asked about using helicopters, didn't they? Why don't we use helicopters? So that's, if you fly helicopters and you do these low-level aerial counts, you're going to disrupt wildlife a lot. There's no way to avoid it. They're incredibly noisy. You tend to be moving a lot slower. I'm not saying you don't disrupt aircraft when you're flying a fixed wing aircraft like a Cessna. You don't disrupt the wildlife, but it is you're flying usually faster, less noisily, and often quite a bit higher. So the disturbance is minimal, and it's really interesting when you're flying along and you come up across a group of buffalo, like that picture I showed you before. It's interesting, especially in a woodland area, the animals don't know what direction you're coming from. They can hear a noise, they can hear a motor, and as you fly up on a group of hartebeest, you might see them. They start to run in a circle. They're not really sure, and then they see you, and only at the last minute might they try to avoid the aircraft. They might try to run away from you, but they'll often run in line with the aircraft, or they'll run underneath you. It's kind of a random movement. It's rare that they'll move directly away from you because they can't even tell what direction you're coming from. And then suddenly you're over them, and then suddenly you're gone, and they'll stop. And you see them kind of looking around, kind of like, oh, what was that? And you carry on. What's funny is that the areas like Tarangire National Park, where there's a lot of aviation, there's a lot of light aircraft coming in and out, a lot of the animals just ignore you. During the height of the poaching crisis, some of the bull elephants who are really, you'd find them in the edge of the protected area, coming back in from outside where they've obviously been disturbed by people in cars, they've been hunted, and they would actually chase the airplane. They would get really upset about you, and they would chase you just like you're driving by in a car. They obviously couldn't catch up with you at the speed you're flying, but they would have a completely different reaction. But a lot of animals will simply ignore you. A question I often get asked is, well, what about chasing animals from one transect to another? And usually the flight distance might be tens of meters or 100 meters after you've gone past. You might encounter the same animals on another transect if you're only going 5 kilometers away. But that kind of distance is not very important when the animals are usually moving randomly in the landscape. They're not fleeing en masse 5 kilometers or 10 kilometers to the next flight line. It's a very, very little concern.
Okay. Thank you. That's interesting. There's another question on what advice do you have for aerial surveying of a wetland bird?
Wetland birds, photographs. You use cameras. It's really, if you're looking at something like just now, I've been working with some people up in South Sudan, and they're counting the shoebill storks up there, but they're very, very scattered. Humans can actually see them and enumerate them. But then you've got things like the ibis and open-billed storks, and they're in their tens of thousands. It's impossible to count them. So using photographic methods. So in a lot of cases, the wetland birds as well you can actually look straight down on them. When you're in a wetland area, there's often not a lot of sorry, that's not true. There could be overhanging vegetation in some places, but a lot of the birds will aggregate in places which are relatively open, so they can take off easily. So doing vertical photography as you fly on these flight lines can work very, very well. So you would actually set up a camera instead of looking out the side of the aircraft. You'd have it set up on the strut or through a belly port, looking straight down, and you would take pictures along flight lines as you fly over these concentrations. Usually a lot higher, and you don't even disturb them; they won't even take off. And that's actually what we do with the wildebeest as well, because the wildebeest. I don't know if Richard mentioned this, but the wildebeest are a special case where you do have a large population which is moving en masse across the landscape. And you end up with a situation where if you counted one survey block in the north and then another survey block in the south a day later, they might have moved all the way through. So what they wait to do is they're waiting for the wildebeest to be aggregated in one place on the shortgrass plains in Ngorongoro, Serengeti. And when they're in an area where they can be counted in 1 or 2 sessions of flying, they then set a bunch of transects in the same way I just showed you, but you set a bunch of transects over that aggregation, and they take pictures of a very, very tight transects of 1 or 2 kilometer spacing taken vertically, and then you count from those photographs. But that's the only way we can deal with aggregations like that, because the human brain is really not good at these really, really big numbers. Anything bigger than 4, we tend to have trouble with.
Mm-hmm. Thank you. So I'll combine 3 questions that was asked during registration. One is, what's an innovative way to delineate ground surveys in remote or difficult difficult access areas, and how can you improve accuracy on that?
Sorry, can you ask that again? I'm not really sure what that means.
What's an
that
innovative, sorry.
Innovative way?
Yes, to delineate ground surveys in remote or difficult access areas. And another asked,
for ground surveys?
Yes.
Well, I don't know about innovative. I mean, the method that I've just shown you is actually very, very similar for laying out sample transects for any area, if you're doing a systematic layout of transects. I mean, the case in a lot of difficult to reach areas, I know that one of the issues with distance sampling, for example, is that you often end up, people have often done distance sampling on transects that were from relatively easy to find areas. And laying out transects in the same way, in a systematic way, even over difficult areas, is extremely important. No matter how difficult it is to get there, some of your transects may take you a day of walking to go and do a 2-kilometer transect. But by doing that, in covering those very difficult areas, even compared to areas which you can do 5 of these transects in one day in the easy areas, you have to do that systematic coverage so that you're not laying out transects, so the transects are random with relationship to the ecological background. It's extremely important. So yeah, I can't think of there aren't, if you find yourself trying to find innovative ways of laying out transects in a difficult area, you've got to ask yourself, am I doing this in a way which makes ecological sense for sampling?
Okay, thank you, Howard. Vincent, do you want to jump in with your question? Okay, I'll just ask on behalf. So are some of the AI and machine learning tech or algorithms being used or tested to automate the counting process?
So we're working on that. I don't know, I think Richard mentioned that we are switching over to using these oblique camera count, OCC systems, where we are using where those cameras that I showed, basically instead of having a human counting and then using the photograph to back up their group estimation, but the human is doing the primary counting. In the future, we're going to be using the cameras, the photographic methods to count everything, where you take pictures consistently all along the transect, and then you count from those photographs. So the problem with that is mainly that it takes a long time to go through those photographs. So an empty picture with nothing in it takes you a good 2 minutes to really go through and look at every single section of it, make sure that it really is empty. And then where you might open a picture and say, oh, there's a couple of elephants there, but it still takes you 2 minutes to go and look at every single part of the photograph. So getting rid of those empty pictures is something which we're really trying to do, where we can concentrate on counting the ones that have animals in them. And what we're hoping to be able to do is to have the computers filter out those images and then do automatic annotation, automatic counting of at least part of the picture of the photographs. I think humans are going to be counting the pictures for years to come. I think the AI systems are going to help us. I'm going to try to pull up a picture while we're talking here to show you an example of this. I think the AI systems are going to be helping us, but not actually doing the counting in the near future. I'm going to try to find you guys a photograph. Oh yeah, here we go. So let me try to share screen. You guys see my screen?
Yes, we can.
So remember I mentioned that the human brain can't do bigger than 4 objects. Well, this would be even more challenging than those buffalo that I showed you before. These are white-eared kob up in Sudan. The males are this really lovely dark brown color with white ears, and the females are all a little bit more impala sort of color and size. But this image here, this is the kind of thing which they've been dealing with in the survey that's going on right now in South Sudan, where as you fly along, you can't even see, there's not a herd as such, there's just this constant mass of animals everywhere outside the aircraft as you fly along. So counting this is what we'd like the computers to help us with. So the next picture I'm going to show you is what the computer had a go at doing with that image. And these are all, okay, I said that. Of course, it doesn't want to move to the next image. Let me try this again. Here we go. This is the computer. This is what the computer did. It counted 1,605 objects in this image. It took the computer about 23 seconds to count this. Now you can see that it got a couple of them right. It says, oh, this is a cob, this is a cob, but in most cases it thought that they were cows. In a lot of cases, it missed animals where there were like a few of them clustered together. Missed a few here, missed one out here in the open. I think there's a couple places where it misidentified. Well, actually, it's done a pretty good. Oh, here we go. Here's it misidentified this clump of grass as as a cow. So this is a little bit silly in some way. You think, oh gosh, it's done such a bad job for some things, but it doesn't really matter, because what we'd really like the computer to be able to do is have a go at counting for us, and then we can correct all of these very, very quickly. We can, select everything and change it to cob. We can go through, but what we really want to be able to do is have a first go at it, and then the humans will do the correction of the work afterwards. So this is coming along. These kind of tools are coming along, and I think, as we all know, AI is rapidly advancing. The thing about these oblique counts is that, unlike a wildlife camera, where the animal takes up a very large percentage of the image. I don't know if you can see my cursor, but I'm trying to drawing like a third of the whole center of this image. Most of the things we're trying to look at in an oblique count are very, very small with relation to the size of the image. As well, compared to looking from straight down or a front-on image when an animal's walking towards a wildlife camera, as the animal rotates, imagine there are all these different positions which are totally different from the perspective of a computer trying to look at this. And also the backgrounds, if we zoom into this part of the image, he said, and for some reason, whenever somebody sends a message, it stops working very well. There we go. In the background here, this background, the computer has to learn that this animal here on this dark background is different to this animal here on the green background. It doesn't understand, the backgrounds are totally different, that the lighting conditions are different. So this counting from an oblique photograph is incredibly difficult compared to counting from identifying a camera trap image. So we're going to have a long way to go yet, but our big hope is that the computers are going to be able to say, oh, there's something here to look at. Please ignore the 55,000 other images which have nothing in them.
Thank you, Howard. So I'm aware we are almost at the hour. I'll just ask one more question on behalf of Rebecca. So it seemed like aspects of the survey are determined by needing to take account of human counters, such as 25 minutes of counting, 150 minutes chip width, etc. Do you think that moving to surveys which capture continuous pictures versus using human counters will enable or alter the sample methodology you're able to use?
Yes, it's going to do a number of things. The number one is consistency. We spend most of our time setting up these surveys training the humans. Humans are really, really good at seeing animals. We've evolved in these landscapes, seeing things all the time. And it's in your survival interest to actually be able to see an animal that's 200 meters away from you when you're walking. So we have this kind of built into us. We're really, really good at it. And yet we're inconsistent. We get tired. We have to be taught how to look into shadows. We have difficulty seeing large numbers of animals. We have difficulty when there are mixed groups of animals. We tend to see one species when we first look at it. So there are a lot of reasons why we're inconsistent. We spend a lot of our time training on how to see consistently in the aircraft. So that's something which will change. The photographs are going to be doing one thing one way the whole time, hopefully. The other thing is that when we can fly higher and faster, we're going to be able to fly more cheaply and cover larger areas in one go. And it should make it 35% cheaper to fly the surveys right away, because flying the aircraft is a very, very large part of the cost. So that's something we're working towards, but we need to understand what the differences are going to be between the humans and the sensors. Because if you think about that graph I showed you of that, over 50 years of data, they calibrated against human eye counts and moving to slides, regular film slides, black and white pictures, digital cameras. At various stages along that trend, they calibrated their equipment to make sure that when there was to make sure the numbers meant the same thing from change in equipment to change in equipment. We have to do that for all these survey areas when we change from humans to using photographs.
Okay, thank you so much, Howard, and thank you for the presentation and for the session, and thank you everyone for joining us today. The recording will be shared in a few days, and you'll be able to access it on WILDLABS and our YouTube channel. Our final Tech Tutors will be next week at the same time, where Jacqueline Booby will answer the question, how do I get started with collecting mobile digital data to combat illegal wildlife trade? So we hope to see you next week. Thank you and have a lovely day and the rest of your week.